Okay, for day 3 of 14.7, we're going to discuss finding absolute maximums and minimums. And it's very much like what we used last year with the extreme value theorem. The extreme value theorem last year, we would find critical values, critical points, and we would test them, find out what that function value is, compare them to the endpoints, and the largest y value would be the absolute max on that closed interval, and the smallest would be the absolute min. The problem is, when we're dealing with functions of two variables, you can see very quickly that we won't just have one interval. We can have regions. And today we're going to look at bounded regions, very similar to what we did with endpoints. A closed set contains all of its boundary points. You can see that this square and circle, they have solid line segments or a solid connection around their shape, and that indicates every point on that set, on the boundary, would be included. If a set's not closed, you'd see a dashed line. Of course, we'd see inequalities describing these regions. Less than would indicate that we couldn't equal the very boundary. But you can even see sometimes a set might be closed on one section and open in the other. We're going to be dealing with just closed sets. Bounded as well. They could always be contained within a circular disk. So the extreme value theorem for functions pretty much says this: if a function is continuous on that closed bounded set, f attains an absolute maximum value and an absolute minimum value at some points x1, y1, and x2, y2. How do we find them? Well, look at this box right here. Very, very similar to the extreme value theorem that we had from last year. First, we're going to find the values of f at the critical points of f in our domain, or in our bounded set. Wonderfully, we don't have to use the second derivatives tests to work this out. We're just going to find those critical points. We're going to find out what the function value is. Then we're going to take the longer part of this problem. We're going to find the extreme values of f on the boundary of this set. And then the largest of these from steps 1 and 2 is the absolute max value. The smallest is the absolute min. So let's very quickly walk through a problem together and see what exactly is occurring. So we have a function, f of xy, 2 plus 2x plus 2y minus x squared minus y squared. However, there is a triangular plane determined by x equals 0, y equals 0, and y equals 9 minus x as a boundary condition. So that's the big difference that we have in today's lesson. I'm going to graph that boundary right now. Of course, going to the xy plane, this would be our domain. These are our independent variables. X equals 0 would be the y-axis, of course. Y equals 0 would be the x-axis. And then 9 minus x, y equals 9 minus x. Well, hopefully you could also see that this would be x plus y equals 9 with x and y intercepts of 9 itself. So we are going to be looking at a triangular region where we are bounded by these three equations. And my goodness, I'm even going to get a little bit of help here and call this origin the point O. Up here, the highest point, we'll call it A. The point on the far right, we'll call that point B. So we have this region that we're only going to be selecting our x, y's from. Our inputs, our ordered pairs x comma y, can only come from here. Well, let's first go ahead and follow step 1 and see if we can do what we've been doing. That's the good news about right now. We can say, well, let's find our critical numbers. Find out where f sub x could equal 0. Let's see, we need to take our derivative with respect to x. We'd get a 2 from the 2x. Obviously, the derivative of 2 itself is 0. Derivative of 2y is 0. And then we'd have derivative of negative x squared is negative 2x. So that's all well and good. Let's take our derivative with respect to y. As we do that, you're going to see the derivative of 2 and 2x cancel out. Derivative of 2y is just a 2. And then from here we can say, well, my goodness, the derivative of negative y squared is negative 2y. For these critical points, all we have to do is set our derivatives equal to 0. We're not even going to worry about the situation where our partial derivatives could be undefined. That's a whole nother issue. Hopefully what you can see for part 1 is that we have now the critical point 1, 1. So if I have the critical point 1, 1, what I'm going to do is actually evaluate what is happening at 1, 1, f of 1, 1. We'll plug in 1, 1 into the original function, and we can work this out very, very quickly. Plugging in a 1 for x, y, you'd get 2 plus 2 plus 2, that's a 6. And 1 squared and 1 squared, well, we would just subtract a 1 and subtract another 1. We would find that f of 1, 1 is 4. In other words, we'd have the point 1, comma 1, comma 4 on our curve, on our surface, I should say. Z, our function f, would have a value of 4. Well, this is part 1. We found our critical numbers, and that's all well and good. But there's way more to this story. Just like last year, you set your derivative equal to 0, find your critical numbers, and we could evaluate our function there. We would always, always, always also check endpoints. Well, you can see by this little sketch that as we look at our boundary, it's a lot more complicated. You see, there are 3 parts to this boundary. First of all, stating the obvious, 1, comma 1 is a point inside the boundary. We're only going to have critical points that fit inside that boundary. Very important to see. But let's very quickly keep going with this. Let's consider segment OA. Segment OA occurs when x equals 0. We're dealing with our boundaries here. Well, if x equals 0, go and plug that into your f. What would f really equal then? Well, everywhere where x could be 0, canceling that out, real quickly, we'd see that we'd have 2 plus 2y minus y squared. So on that line, x equals 0, our function f becomes considerably more simple. Well, now, let's very quickly see what's occurring. I could take my derivative. This becomes just like a problem from last year. I'm down to just a function of 2 variables in this regard. Let's take our derivative of f with respect to y. We could very quickly see we'd have 2 minus 2y. 2 minus 2y when we do that. If I set that equal to 0, very quickly we could solve, and we'd say, well, wow, 2y is equal to 2. We'd get y would equal 1. But please understand something. We don't have the ordered pair that we had before. We're going to have the ordered pair 0, comma 1. And the reason is, my goodness, x is equal to 0 here. So we have 0, comma 1. And by the way, we could very quickly, might as well do this, say what exactly happens when I plug in f of 0, 1. Well, you could even go back up to this function right here. We already saw what happened when we plugged in 0 for x. When we plug in a 1 for our y, let's see, we'd have 2 plus 2 is 4, and 4 minus 1 would be a 3. So we have a z value of 3 here. Well, what else do we have to do? Well, look at segment OA. At segment OA, we also have some endpoints. We've got the endpoint of 0, comma 9. We also have the endpoint of 0, comma 0. And we should see what's happening there. Now, this is all occurring on the line x equals 0. So, believe it or not, I still could use this simplified equation that I found by plugging in x equals 0. If I want to know what my f value is by plugging in 0, 9, don't get me wrong, you can certainly plug in 0, 9 into the original, but why not just do a little bit of work here? Plug in a 9, you'd get 2, let's get that back. You'd get 2 plus 2 times 9 minus 9 squared. Well, that's 2 plus 18 minus 81, and 2 plus 18 is 20. 20 minus 81 would be negative 61. So this z value would be negative 61. Hey, plug in 0, 0 into the original function or into this green highlighted form right in here. Just let y equals 0. You'd quickly see that your z value would be a 2. So what are we getting at? Well, this is only one little piece of the boundary, guys. We've just got these following potential max-mins. Well, guess what? There's more to the story. We could also take a look at another piece. We could say, what about 0? How about OB? OB was where y was equal to 0. And if y was equal to 0, go back to your original function, and everywhere where you'd see a y, you replace it with a 0. Well, you can see very quickly you get something incredibly symmetrical to what we just did a moment ago. With OB, we've got this worked out. You can say take your derivative of f with respect to x, and we'd have 2 minus 2x, and you'd see that we would get a critical number of x equals 1. Well, here we go again. This is 1 comma 1 for x, but y is 0 on this segment. So we could say that we have the point 1 comma 0. Well, let's find out what f of 1 comma 0 is. Here we go again. You know what? We could substitute everything back in to the original function. Why don't we just take it easy on ourselves and use this simplified one? Let x equal 1 into that 2 plus 2x minus x squared. Once again, you'd get a 3. So we're seeing a lot of symmetry here. Here's the other thing. Are there any other endpoints on this that I didn't already refer to? Well, I took a look at 0, 0 in the last segment, but I do have the point 9 comma 0 on the right endpoint of segment OB. So I'd like to find out what's happening there as well. And if we did f of 9, 0, well, work this out. You know what? Plug in a 9 into this equation. It's just like what you had plugged in previously, plugging in y equals 9 before. You'd see that you'd get negative 61. So what are we really getting at? We've got some other candidates, 2 other candidates for absolute maxes and absolute mins. Well, there's more to the story. You might guess there's still segment AB. Now, the wonderful thing is with segment AB, you already have the endpoints from the previous cases. You have 9, 0 and 0, 9, but we do have to investigate what's happening when y equals 9 minus x. Well, my goodness, we could do that real quickly. Let's consider then, here's segment AB, and we're going to have y equals 9 minus x. Well, this is going to be the most work that you're going to see. I don't think it's really too much of a surprise. Wherever we see a y, we're going to replace it with 9 minus x, and we're going to have to work that out. We're running out of time, but maybe we could real quickly get a little bit further. Working this out on the TI-89 would be an option, of course. Let's see, expanding this, 9 minus x quantity squared is 81 minus 18x plus x squared, but we're going to have to distribute that negative. Wow, look at that. Okay, I think we're about to run out of time, but suffice it to say, we're going to keep working here, finding critical numbers We're going to pick this up in part 2 in just a minute.